Hi friends, welcome to my YouTube channel, and this is a completely new lecture series and new lecture videos I will talk about one by one, and this will complete the whole lecture or whole topic concepts about the time, how the timing things work in digital circuit, mostly in the digital VLSI we are talking about the STA. But here I want to discuss more about the STA, more about the timing, delays and all. So let start with the lecture. There's a two agenda I am saying today, like I'll try to cover. The first thing, simple thing is like why the timing is needed. So think about our own life, own personal life, because we always talking about like in our own in general work, we can't expect or you can't afford that any work is done by some delay with some delay. So same thing in computer. Like in computer do the computation. In computation, we cannot also afford that the computer do their computation in with some delay. So delay is a very crucial things we always need to take care about that. And from that delay, you all know the simple term is you all know the how the delay and the frequency is related. They are inversely proportional. It's simple. You all know that. So the main purpose is like because ultimately when you are talking about the computer, when you're talking about any computation things, so ultimately you're talking about any architecture. So based on that architecture, you are actually know that you are realizing it as a digital logic with some combinational and sequential element. So they have to run with some clock frequency, with some delays, because every block, every element, there have some own delay to propagate the data from one end to another. So that's why the frequency is ultimately connected with the clock frequency, or sometimes the clock cycles, how much the clock cycle the data path or the logic is taking to go in the valid state, like proper output when it is given. So that's the one point. Another point is like because we are ultimately talking about the IC part. So ultimately your any IC is running with some clock frequency. So as I said, like my core, this is a um, two core IC. So this is running with some 1.8 gigahertz frequency. So this means what? This means like we have to ultimately find what is a safe frequency to run my logic, and I am achieving that with with my designed architecture. So that is the one point. Like what is a safe frequency here? And ultimately, as I said, that we are ensuring the timing safety. Okay, but the things is like always we when we study the timing, so that time we talk about the simple things like static timing analysis, dynamic timing analysis, and their various calculation with maximum path delay and all. Those are there, but I will cover one by one in the lecture. But before going to deep dive into the timing calculation, estimation, and all, I need to talk about the design flow. Like in the any design flow of our IC or chip we follow, primarily, what is the ultimate? What is the ultimate like? Which part we actually talking about the time? We always talking about the ASIC design flow, but also there is some called full custom design. Okay, full custom design, semi custom design, standard cell based design, and standard cell based design. Then like what I can say, FPGA based design. Maybe their whole design flow is little bit different from every other, but in general we always follow the ASIC design flow. So I before as I said before going to deep dive into the topic, so I want to discuss that uh, actual what is the ASIC design flow we are following. So the simple things like we all know when we start with design or user specification, what the users want, like what the customer actually want from us. So because they give maybe they give some working function, or they give some software algorithm, and based on that we need to decide the what is the architecture, like pre-architecturing phase we are talking about. And this is a very rough estimate the- of the design. Like generally we this part we generally talking about, like how many adder we need, maybe how many divider we need, these things. It's not a very uh, particular thing that we know for this function we have to follow this type of things. So this is a pre-architectural part. And then the famous part we all know, that RTL coding and design, because most of us we generally study the Verilog code, so that's why we know that how the RTL coding is done. Because whatever the block you decided in the architectural phase, that block you have to one by one code, or that block you have to one by one design with your logic. So that's why HDL coding is done. But the design is done, but how you have to verify that your design is specifically safe to run, or your logic is properly, it is giving the output from every block. So that's why the verification and simulation is very much needed of the whatever the RTL design you done based on that. And there is several languages also we always follow, like system verilog is a very famous language. Then whatever the design, whatever the after verification or everything you done, that part you are just synthesize your design. Like you need your netlist part, because whatever the design you done, that you have to synthesize in the gate level or logic level, and based on the synthesis, there the netlist will generate. Okay, so this is the somehow this is we can call this is a whole part of the front end. Mostly here we don't need that timing, but throughout the process we can design the power timing our design. We have to make this much criteria of the timing budget, so timing our design you can done. Now coming to the one part, that after that netlist you got, you can do the logic ST part, because by that time you only, by the netlist you got is a logic type of netlist. You know that it is a gate level not netlist, or the logic level netlist. So by that time you only done what, you done only the logic static timing analysis. Then you add the DFT part, whatever the design for testability. Then the main backend part is started after that, which is very important, because most of the timing things we follow here. Why? The physical design step, as I said, like here physical design step is started. The physical design state very well known. I think you all know. If you don't know, maybe some video I'll cover, I try to cover. But mostly we follow the partitioning of our netlist, because by the time we already got the netlist. So that's why based on the netlist we done the partitioning, then floor planning, then placement, then CTS means clock tree synthesis, then the routing. Routing has a several parts, like every steps have a different maybe algorithms, different steps. But routing we know that global routing, then detailed routing, then grid routing, all are there. But obviously I am not going into detail. But the things I try to tell here, that every steps of the physical design we try to like check the timing is met, timing part is met or not. So that is the whole purpose I am talking about. Like every part we are checking about our timing, every part we are checking about the static timing analysis. So maybe after that routing you will get your design layout, but this design layout is not a fully optimized. Because why? Because maybe some of the steps you are uh, overlooked, or maybe the timing part is not made till now, or maybe the power things also maybe not properly done. Maybe routing there is some little bit of layering or net routing is mistakenly done. So that's why this design layout which we will got, we cannot directly send to our fabrication. So till now we got the not fully optimized netlist as I said, but after that we have to go for some post layout verification steps. But before post layout verification, we have to do the proper layout extraction. That layout extraction is done by circuit extraction, parasitic extraction, and technology pre-characterization. Circuit extraction means that whatever the design you have done with your up to the physical design part, up to that physical design part, routing part, that the merge or merge GDS we have to extract. Then the parasitic, mainly the RLC, those information we have to extract. And the technology pre-characterization is uh, your design your design which node properly we want to operate in the fabrication, that maybe the N3 node or N5 node, those things. And also we can do the curve fitting, sampling, mostly the statistical part of methodology we can done in the technology pre-characterization part. The most important thing is a sign up series of sign up checks. In that, the STA, that STA, like static timing analysis, is very very important. And that static timing analysis is important because this is the last chance you have to properly check the timing you are following in in your whole design. Then you can ready for send to the send for the fabrication. Other than that, there we done some physical verification checks, signal integrity check, power integrity checks, maybe some other checks also. But physical verification checks is whatever the physical design you have done, maybe this design you done with your with some rules, and that rules also satisfy with your with the rules which is coming from the fabrication industry also, like the net spacing, net width, mostly those checks. So there, the design rule checks, electrical rule checks, and layout versus schematic is the most doable jobs we generally check. Other than that, signal integrity checks is that one. Suppose there is a two net which are running parallelly. Between that, maybe they are carrying another signal, but between that two nets, what is the capacitive conditioning load impact? We are checking that. So for that, signal integrity part we mainly check the crosstalk noise, base delay. Other than that, electromigration and IR drop checks. But EM and IR checks also we have done in the power integrity part. uh, in the power integrity we also check the noise, ripples, impedance issues, those things. So mostly series sign up checks is that part which actually we have done to get proper fully optimized layout. So maybe by that time, what are the optimized layout you got, that layout is sufficient to uh, sufficient for tape out and send to the fabrication, send for the fabrication. If you want to change some of the incremental change you want to do, but not in the deep design, but some incremental change you want to do, that change you that change you can do by the ECO process, which we called as a some engineering change order. This is actually the small incremental changes. Then mostly by that time, you already got the proper optimized layout. The GDS file we can send to the fab process. So we complete that whole lecture. The whole lecture main motivation is to tell you that which part we actually do the STA part. One is the logic STA, one is the STA we have done in the whole physical design every step, and one is the STA in the series of sign off checks. So thank you to listening for my videos.